You launch OSIRIS-REx from a moving platform, Earth, to intersect a moving target, Bennu. You do a touch and go, grab material, come back to Earth. All this has got to work out.
We got there, we screamed because there were boulders 11 stories high. Several stones got caught that we were losing sample every time we articulated the arm.
Wow.
There's another PhD thesis. There's another PhD thesis. Come on. It wasn't quite what we expected.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Chuck Nice is with me in the house.
Yes.
Chuck, how you doing, man?
I'm good. I'm in my house.
You're in the house remotely. How you doing, man?
I am doing great.
You know what we're going to do today? Something I think should have done long ago. We're going to take a look at the ingredients for life as they exist in the rest of the universe, and how some of those ingredients may have influenced what happened on the early Earth.
Nice.
Yes. And we have a record of what the early solar system was like, and it's contained within our comets and asteroids. They've just been orbiting the sun since like day one. Right. And they haven't been absorbed into a volcano. Yeah. They haven't been rained on. Right. They haven't been peed on by any animals. And so there's a pristine...
I've never considered that as a...
I know, right? That could totally
as an obstacle for finding our origins. Well, you know, we would have found out, guys, but unfortunately, do you see how much deer pee is on this?
So we have one of the world's experts in this, Harold Connolly Jr. Harold Connolly, welcome to StarTalk.
Oh, thank you so much for inviting me. It's a great pleasure and honor to be here.
Excellent. You're founding chair. I love those. Chair and professor in the Department of Geology in Rowan University, and co-investigator, COI is the abbreviation of that, and mission sample scientist for the OSIRIS-REx mission.
Ooh. That's big stuff.
I know. So first of all, we have to give the test. You have to give every principal investigator. Okay. Please tell us what OSIRIS stands for, because it's an acronym.
Okay. But I'm not the PI, just mission sample scientist.
Okay.
As one level
You're just the
me.
guy that analyzed the sample return.
Just the guy that conducts 260 people around the world. But yeah, so OSIRIS-REx is NASA's New Frontiers 3 asteroid sample return mission. And it stands for Origins, Spectral Interpretation. See, now my brain is fried because I'm laughing so much.
I told you, it messes with us, these tortured acronyms.
Origin, spectral I think I know it after all these. Spectral interpretation, resource identification, security, and regolith explorer.
Oh, okay.
Wow, okay.
Wow. That's cool.
Yeah, that's very tortured right there. Well, that's no. Next time, I'll help NASA next time they need an acronym.
Origin, yeah, right. But Origins is easy, right?
Right.
Yeah. We got that. So the thing is, we know that asteroids have hit Earth before, and we call them meteors coming through the atmosphere, meteorite when you pick it up. And so we have quite a large catalog of space rocks on Earth. So what is your motivation for going to an asteroid that's out there in space?
That's a great question. A couple of motivations, and they're fit into that strange, acronym we just discussed. And there's one particular branch of meteorites, which I'm just going to show you both right here because I'm holding up my hand, which is known as carbonaceous chondrite. There's several different kinds of meteorites we have on Earth, and these are really old. This is what gives us the age of the solar system, the 4.567 billion years old.
Wait, you're putting your grubby hands on a meteorite.
Listen, Neil, if it made it this far, if it made it after 4.7 billion years, I don't think Harold's fingerprints are going to screw it up.
My boy just finished eating buffalo wings, and he's licking his fingers, touching this hunk of coal. Okay,
well, we'll get back to that, but that's a great point. But this one comes from sub-Sahara in Africa, so it's probably had camel dung in it at some time. follow our analysis or analog earlier. Anyway, so yeah, the key is we don't know exactly what meteorites come from what asteroids. We have some spectral identification, meaning we look at different wavelengths of light and we identify asteroids. And we want to be able to understand the geologic context of these meteorites, because any rock the geologist has, you can only tell so much about the story without putting it into the chorus that it's been singing in to know what is the larger picture. Furthermore, these carbonaceous chondrites are full of what we call volatiles. They have water in them. They have minerals that require water to form. They have organic compounds in them, the prebiotic compounds that we need in order for life to have developed. And those are some of the key issues, including, as we said, security, which is we don't understand exactly how asteroids move very well, because we make these predictions about how they're going to possibly hit the Earth in the end of the 22nd century. And we have what we call a probability, but that probability also needs to know what's the composition of the asteroid in order to predict well.
Oh.
But let's back up for a second. The geologist, first, let me celebrate the fact that geologists are now holding hands with astronomers, astrophysicists, to explore the rest of the universe, because we're trained to look up, and we're not trained to understand rocks that might be at our destinations. And so we tag team with you geologists to help us interpret what's out there. But you use the word volatile in a way that the general public does not. To us, if something's volatile, it's like ready to explode.
Unstable.
So, very good point.
Yeah, tell me what you mean by volatile, that a rock would have volatiles.
Yeah, so when we talk about rocks that have volatiles, and we're talking about the kinds of compounds that would quickly evaporate when you raise the temperature of the rock from basically background temperature.
Oh.
Yeah, so water, for example, everybody knows water will boil, at 100 degrees C or 212 Fahrenheit. So, that's something that these rocks contain, and that water is 4.567 roughly billion years old, and was moving around the actual original body, what we call the parent body of the asteroids that we see now. What we see now are basically bits and pieces of what was once much larger bodies that were internally geologically active.
Interesting.
Wow. Okay. So so it's a time machine for you.
Oh, definitely.
It's a time capsule. Capsule. That's right.
Capsule, better word. Yeah.
And going back to your analogy of the dog pee, many of these, in fact, they get contaminated, the meteorites, as they fall to Earth very, very quickly. So within a day or two, you've already contaminated. You're interacting with the atmosphere. Little microbes start to eat them. I mean, imagine you're sitting around for 4.5 billion years, as Neil said, and you've got nothing to do, nobody to bother you really, except occasional collision and the sun hitting you. So the other idea is to bring back a sample of pristine material, keep it in a nitrogen environment and analyze it. And that turns out to be, as we'll see, absolutely critical to what we have been finding in both asteroid Rugu sample and, of course, asteroid Bennu sample.
So let me start some trouble. Yeah. What will we find more from? Because a comet has the water, it's ice, right? So what would we benefit more from? A sample collection of an actual asteroid, which we've done. That's what you guys did. Or being able to kind of either trail and capture or capture a piece of a comet, which will give you the water.
Well, that's a great question. And capturing the water and bringing it back to Earth is incredibly tricky. We have sampled from the back of comets in its coma and brought back the minerals that were actually in that comet material, but not the ices. To actually freeze a sample and bring it back is really complicated and really expensive, most likely.
So you're saying it's hard to bring back the volatiles is the point here.
It's hard to bring back the volatiles and the ices and stuff because you got to keep them cold the whole time and keep them cold coming through the atmosphere and then not interact with their Earth too much. Actually, this brings, stop me if you want, but this brings sort of a square root of one question, is that the OSIRIS-REx mission is a special class of missions, which is a sample return mission. Of which, if we don't include the Cold War, Apollo and Luna samples, we've only had a couple of handfuls of those in the course of history. Basically, 3 of them by the U.S., 2 by Japan, and 2 by China. So you're looking at basically a large sack of potatoes of extraterrestrial material that was brought back to Earth, roughly 8 pounds or so of material. That was a little over $2 billion worth of money spent to get these samples back for a scientific community that conservatively probably only 100, maybe 1,500 people in the world work full time at trying to understand.
I don't have a problem with that.
I don't. Last year, the American people spent $4 billion on candy for Halloween. So, here we're pushing the frontiers of our origins, understanding where we come from.
The dentist needs you to spend that much on candy. Okay,
I have to get a crown tomorrow. I have to get a crown tomorrow before I move to England for 3 months. Thank you. I know.
Right. So let's back up again. Of all the asteroids that orbit the sun, most, of course, are in the asteroid belt. Those are harder to get to, I guess, because a whole bunch of them cross Earth's orbit. So one of them you picked, I happen to know, Bennu crosses Earth's orbit. So is that what makes it a little more attractive and because of how accessible it is?
100%. Our scientific goals were to get to an asteroid. Well, our goals were to get to an asteroid that we could get to safely and come home, and that was within some kind of cost cap or wasn't cost prohibitive. And that asteroid we determined to meet our scientific goals has to be a carbonaceous asteroid because we needed to look for what we know already is contained within the asteroids, fragments, meteorites, scourge of life, volatiles, etc.
And just to contrast that with what many people stereotype as an asteroid, a metallic asteroid, and here at the American Museum of Natural History, our 2 biggest asteroids are iron and nickel, and they're huge, some of the biggest, out there. And so many people, when they just come to, to a museum, it's the metal ones that get all the attention, because the other ones just kind of look like rocks, frankly.
Because they are.
Because they are. Is that why they look like rocks? It seemed to me that it would be harder to sample return from a metallic asteroid because you can't sort of pick up dirt on its surface. Is that a true fact?
I think that's right, Neil. Yeah, we have a mission. NASA has a mission going to study asteroid Psyche, which is supposed to be an iron nickel asteroid, but it's not bringing sample back. It would be a lot harder to drill and actually get a piece of metal out of the asteroid and bring it back.
Just Bruce Willis could take care of that. No problem.
No problem.
Okay. So we go to this asteroid. If I remember correctly, this mission was a touch and go, right?
Perfect. Yep, it was.
Yeah, and so it comes down, punches up some material, captures it in a capsule. When I rethink what this mission did, I'm just saying, as a matter of fact, it is rocket science, right? So you launch OSIRIS-REx from a moving platform, Earth, to intersect a moving target, Bennu. You do a touch and go, grab material, come back to Earth, deploy the capsule onto a rotating Earth so that it lands where?
Utah desert.
In Utah, okay.
As well it should.
And a gentle plop, nothing else.
Wow.
Right. So of all, on the rotating Earth, all this has got to work out. And then that's when my worst nightmares begin, because one of the earliest novels I ever read in my life was Michael Crichton's The Andromeda Strain, where they brought back basically a sample return from, I don't remember where, just from space. And it had a bug that started killing people. And so let me ask you, tell me about NASA's protection protocols for this.
Yeah, that's a great question. So the asteroids are considered non-hazardous with respect to any sort of biological threat. They've been sitting in space for 4.5 billion years and been cooked by the sun's radiation and cosmic rays in the background on the surface, and are deemed not hazardous with respect to any kind of biological issues, right? So planetary bodies like Mars, that's a whole different issue and requires a whole different set of responsibilities and care that have to be taken if you want to bring sample back from there.
So the pictures I saw with people analyzing, maybe your hands were among those, inside that sealed cavity where the dust from the capsule was getting analyzed, that was really just to prevent a sample contamination, not to prevent you from getting some kind of bug.
Right, being contaminated by some kind of alien. Now, with that, Harold, have you had any compulsions since you've handled this material that you have not understood?
As a matter of fact, yes, I drink less gin than I used to.
Oh, okay.
All right. T-Mobile 5G home internet has some big news you should know about. They now have the fastest 5G home internet according to the experts at Ookla Speed Test. Now, in practical terms, it means photo backups happen faster. Streaming a documentary doesn't stall halfway through. The physics of waiting reduced. What's also notable is that this jump in speed doesn't come with added complexity. Setup is simple. You plug it in and you're online in less than 15 minutes. And the value side of the equation holds up too, with a plan price that's backed by a 5-year price guarantee. So, if you want the fastest 5G home internet with a simple setup and savings that stick, get T-Mobile 5G home internet. Just visit t-mobile.com/home internet to check availability today. Price guarantee, exclusions like taxes and fees apply. Fastest based on Ookla Speed Test intelligence data, second half 2025. All rights reserved.
How much meteorite material did we bring back?
Roughly 122 grams of material, and that's basically, sounds like it's small, but it's basically a cup full of particles. But that cup full of particles is a lot.
That's
correct.
a lot.
It's a lot. Yeah.
I was going to say, but now when you make the collection, because it is a rock, and I don't know a lot about rocks, but I know some rocks are harder than other rocks. And I also know from a conversation with Neil that some asteroids are kind of like pebbly because they're held together. They're not really a big solid rock. They're kind of pebbly and held together, and it's easy to go in and do whatever you want to do. If we were talking about mining asteroids, if I recall the conversation.
Yeah. So Chuck, very important point there. So Harold, what was your confidence in the structural integrity of Bennu to just come down and do a touch and go? Did you know enough about its structure to know that would succeed in advance?
Yeah, great questions from both of you. And, first of all, Bennu is what we call a rubble pile asteroid. So it's literally an asteroid made up of accumulation of large boulders and teeny tiny little grains. And it rotates around its own axis in 4.2 hours. Actually, it rotates retrograde, which means opposite than what we normally would think it rotates. And all the information we had designed originally the spacecraft for big ponds on the surface of really fine-grained material. We're talking about less than an inch size material because our data, our science showed us that there should be a lot of it. We got there, we screamed because there were boulders 11 stories high. And it wasn't quite what we expected.
And you can't fit a boulder 11 stories high into your canister.
Well, we can't. It's not that big.
Well, bigger boat.
Bigger boat.
And, the problem is when you fly down to the surface of the asteroid, you may not come back out the same way either. So there's challenges with the navigation that you have to think about. And to get to your questions and your comments here, we had designed the touch and go sample acquisition mechanism to basically just touch the surface, as Neil said, and we fire some nitrogen gas, and it basically fluidizes or moves the gravel up, and then it gets collected into this little sort of reverse Hoover or vacuum head, and then we would pull back. The autonomous spacecraft pulls back from the surface. But what happened is we went in 48 centimeters, length of an arm almost, down into the surface of the asteroid, which wasn't, went right through it, boink, which we did not really expect. Some folks on the mission will say, well, we had some models that showed it could be, but yeah, okay, it could be. But that was a good thing actually, because it taught us that gravity itself is basically what's holding the asteroid together. Tensile forces between particles is not really doing it very well. Hey, Neil, see, I learned some physics over the last 20 years. And, and the other thing is we're penetrating deeper into the surface. So the surface of the asteroid is being cooked a lot, depending on how much the surface is moving based on the rotation and landslides and impacts. So we're getting down to the stuff that might be fresher, quote, fresher.
So that's better for you.
Correct. Absolutely correct.
Wow.
The problem was, and you did ask another question there when I get to that. The problem was that when we pulled back up, and did the first test to see what kind of sample we got, we literally moved that 3-meter arm backwards to a camera to take pictures. And I can remember about 4 o'clock in the morning, waking up and downloading from our mainframe the images and start looking at it. It had all these little spots all over the place. I'm thinking, what the heck are these spots? Long story short, as the world knows, several stones got caught, keeping the flap open. And that we were losing sample every time we articulated the arm.
Wow.
There's another PhD thesis. There's another PhD thesis. Come on.
That's tough.
Yeah, always right.
That's tough.
So, yeah, that was so the PI had to make some quick decisions with the associate administrator of NASA and other people to basically stow the sample much quicker than we had expected to prevent more from loss. But of course, as you know, we got 122 grams of sample, 121.6, and we needed to get 60 grams to meet our scientific goals.
That's a success.
Yeah.
That's a success. Yeah. Hey, so you bring it back to Earth, and now you've got it in the lab. And so you're a geologist. I don't know. Do you guys use microscopes, or do you use stuff that dissolves the material and you do mass spectrometer? What's a geologist's dream lab when you have something from space?
That's a great question. We brought the sample out of the field. By the way, the sample canister, the SRC sample return capsule, landed in the Utah desert basically perfectly in the end. It had rained there 3 days earlier, but it chose to land in a dry spot, which was perfect. And then we take it to a makeshift facility at the UTTR, Utah Test and Training Range. We get the sample canister and it's, the guts of the sample return capsule out and get it under nitrogen so that the sample is constantly bathed in nitrogen. So, that took literally almost 4 hours to the mark to get that under the perfect timing.
A quick chemistry question.
Yeah.
You speak of nitrogen as though it's neutral. And in fact, there's some sort of wine air replacement canisters that send nitrogen in as the air comes out. But to me, nitrogen can make ammonia, nitrous oxide. It's not like argon, where we're taught in chemistry class is just inert because it's got no electrons available.
Just nothing to do. No interaction.
Nothing to do. So why does nitrogen work for you? I just never understood that chemically.
In this case, we have the samples of the nitrogen, so we know what the composition of the nitrogen is. Not just nitrogen, but its isotope composition. If there's any impurities in it, which of course is not, and it doesn't react with normal minerals and rocks in any way, shape, or form.
Okay.
I shouldn't say normal. I shouldn't say normal. There's nothing normal about
Typical.
an asteroid sample. Typical.
Typical.
And then we get to I'll just tell you real quick. Then we get to the lab. We open up the canister, and the first thing you do as a geologist is you look at it with your eye. The most important thing is that it's a rock. Before you begin to slice it up to make polished sections, before you send it off to the folks at Goddard Space Flight Center to analyze organics, before they dissolve it up to get their analysis, you must know what the rock is, because the context is absolutely critical. Without the context of the rock, you may not be able to interpret your results.
So different labs had different objectives in the samples that they were given.
Correct.
Okay. Is it possible that your priors, I don't mean to get philosophical on you, but is it possible that your prior expectations for what the sample is can bias your conclusions that you draw from it?
100%. We had if I may, we had an amazing aha moment when we discovered, which we should have more or less known we were going to discover, but because we find so few of these minerals in meteorites that we pick up on Earth, it didn't kind of process that the asteroid samples could be rich in evaporite minerals. What is an evaporite mineral? A mineral that forms in a water-rich solution as that water evaporates. A classic example, table salt.
Right. Absolutely.
Table salt is in the rocks from Bennu. It's in the rocks from Rugu.
Wait,
and the point is,
so is the Utah Salt Flats, and it landed in Utah. So there.
we have samples to prove it's not from there.
I'm just saying, you land in Utah and you say, we found salt. Just to alert our listeners and viewers, when a geologist analyzes a sample, in most cases, the sample is destroyed when you're done. Isn't that correct?
Well, yes and no, actually, because I'm the kind of geologist that's called a petrologist, and my job is to tell the stories that the rock contain. And that means looking at them with my eye, looking at them with a microscope, as Neil said, and then actually cutting them and polishing them and looking at them with a special microscope, either one that's optical, that sees through to the thin coatings of the rock on basically a glass slide, or put them in an electron microscope or a scanning electron microscope, where then you begin to analyze in detail their composition of the minerals and how the minerals arrange themselves and why they're the way they are. All these little details, it's like being a detective. The tiniest little clue may actually open up a whole world of being able to understand geology. Now, other scientists do dissolve sample. But if you dissolve the sample without knowing what you dissolved, other than it came from this mountain, I mean, how many different layers of rock are in the mountain? And you say it came from that mountain. Well, I don't know where it came from. That doesn't help you recreate the geology and then put it into context of a special question, such as, looking at the potential origins of what we know is like.
So I don't mean to diss your entire profession, but most people, when we look out into space rocks, we're kind of interested in the organics, not in the minerals. And I know geologists love them some minerals, but at the end of the day, the headline is not what kind of new rock you found. It's what kind of organics might be there. Yeah. So how close were you to that analysis, or was that a whole other group?
So that's a very good point you raise. And the problem with the organic chemistry, well, not a problem, but the challenge is that you have to know what the rock is that you're analyzing. What processes, geologic processes has it been through? In order to know the geologic processes that rock has been to, in this case, in a parent body that was probably the size of Ceres, the asteroid Ceres, for example, that fluid moved through that asteroid 4.5 billion years ago because the asteroid became active. When the asteroid accreted rock in the earliest time period, it accreted ices, not just water ice, but ammonia, carbon dioxide, carbon monoxide, etc. And then the asteroid internally began to heat up, and you have fluid moving through. Now, why is that any relevance whatsoever to prebiotic compounds? Because prebiotic compounds may very well have formed in that aqueous or water-rich environment. The evaporite minerals that we talked about are the late stage product of the fluid that moved through, that formed other minerals first, and they're the very last stage. Now, if you're an organic chemist and you want to get organics to come out of a solution, one of the classic methods of doing that in the laboratory is you salt the solution. And the organics go with the evaporite minerals or the salt when you evaporate the fluid.
I got to correct you on something. You called Ceres an asteroid, but it got promoted to dwarf planet.
Dwarf planet.
You're right. I'm sorry.
Just get with the program here.
I'm sorry. I'm behind 30 years, right?
Just remind people it's the only asteroid that's large enough for its gravity to have shaped it into a sphere. And that's a sufficient qualifications to be a dwarf planet, just like Pluto.
Yeah. By the way, Pluto sends its regards and says "F you."
Thank you, Chuck, for that.
Poor old Pluto. Poor old
for that telegram. So what do we know? I seem to remember a research paper, or it might have just been a review in the New York Times that talked about. Was it amino acids that were found in the rock?
Yeah. We've found a lot in the rock, and we're finding more. And they also, found a lot of organic compounds, because we're talking about organic compounds, and the minerals associated with them in the Rugu sample. The difference is that in Hayabusa 2, which was the Jackson mission to asteroid Rugu that brought back sample, they brought back 5.2 grams. So they have a lot less. So for us, we were able to do work for organics on individual stones from Bennu, and also homogenized powder of more than 6 grams that we homogenized up to really understand the chemistry well. And indeed, they have found that the main headlines is, 14 of the 20 amino acids that are needed for life, but really it's probably 15, because a paper by Mahara et al. That came out in November found the 15th one, and we have to reproduce it, but that was right near Thanksgiving, and that 15th one was tryptophan, which is the same stuff that you get in turkeys that make you sleepy, right?
And that's why Bennu rotates so slowly.
Thank you, Chuck, for that scientific analysis. When is the paper coming out on that? I forgot that tryptophan is an amino acid. I've forgotten that. And the famous one from Jurassic Park is, of course, what is it? Lysine.
Lysine.
We wanted to make sure that the dinosaurs were dependent on that, and therefore they would die had they escaped. But of course, together now, life finds a way. So Harold, I remember, because I'm that old, back in the 90s when we analyzed ALH 84001, something like that. This potato-shaped meteorite on Earth, which was deduced that it came from Mars. And I thought it was brilliant. They found a little air inclusions within it and analyzed it, and had the exact atmospheric composition of Mars. So this rock came from Mars, and there was no dispute about that. But it also had some inclusions within it that, if memory serves, it had oxidized minerals sitting right adjacent to non-oxidized minerals. And typically, in any geologic environment that you have, it's either oxygen-rich or not, right? And if it's oxygen-rich, then everything gets oxidized. And if it's oxygen-poor, then nothing is oxidized. But life does both in the same vessel, right? We inhale and oxidize our hemoglobin, and then the oxygen gets ripped away. Hemoglobin goes back for more oxygen. So we have oxidized and non-oxidized molecules in the very same vessel. So the fact that they were together on the rock would require you to believe, if you're going to explain it abiotically, that the rock was like over here for a while and was getting oxygenated, and then it rolled somewhere else where there was no oxygen, and then it had some other participating molecules. You have to really Rube Goldberg your way into that answer.
Or it was breathing.
Or it had lungs.
My fault.
So with these inclusions at this new site on Mars, at the Chiava Falls site, if you find more than that, it might be really hard, if not impossible, to completely explain it abiotically. So do you know what else was discovered in those inclusions?
Yeah, so the report the report talked about basically the byproducts of breaking down fatty acids, if my memory serves me right, and alkenes, and some single sort of chain organic molecules. And
we don't want any fatty rocks on Mars. We don't want any fatty rocks.
No, we don't want them getting too
Said Pete Hegseth.
No fatty. We'll take some acid, but no fatty acids. No.
Well, I think that's one of the other data points that they're using to, the scientists who wrote that paper are using to argue that there's additional evidence of potential biological processes that were around at that time, 80 million years ago, which is the Cretaceous period here on Earth. So here on Earth, dinosaurs would have been walking around at that same time period. And that's a lot younger than the 84, Allen Hills 8401, that rock is, because that's about 4.1 or 2 billion years old, that rock. So the likelihood, at least more confidence can be given that that's a nicer way to construct a hypothesis. But again, we still have so much to learn about the formation of organic compounds in the relationship to geology and the rocks. And to go off too much in one direction or the other, I think the middle path is required here.
Rugu, whose mission was that one?
So the JAXA, the Japanese Space Agency, has had two sample return missions. Hayabusa 1, which went to an asteroid called Itokawa and brought back teeny tiny little grains because the collecting mechanism didn't quite work the way it was supposed to. But then Hayabusa 2, which went to the carbonaceous asteroid Rugu, which was actually OSIRIS-REx's backup plan in case we couldn't figure out how to get to Bennu. And they chose Rugu and went to Rugu and came home basically earlier than we did. The analysis started in June of 2021, and I was living in Tokyo at that time period for the beginning of the analysis of their sample from asteroid Rugu. Now think about that. It was a pandemic.
Yeah, of course.
I was crazy.
Isn't Rugu the name of a Star Wars character? I have some. It ought to be if it's not.
It's a pretty cool name, yeah.
So just to sort of celebrate the scientific profession, tell me what role the researcher Rugu played in your guys' approach to Bennu, because one mission stands on the shoulders of the previous mission. That's how science works. So were you able to answer or ask different questions of your samples because of what was learned in the previous sample returns?
Yeah, it's both scientific, engineering, and cultural in the exchange. We had co-eyes on each other's team, which means members of each other's teams. I was a member on both teams, and Shogo Teshibana from the University of Tokyo was a member on OSIRIS-REx, as well as in charge of analysis of sample for Hayabusa 2. And indeed, the early analysis of their sample, which they analyzed only 100 milligrams of, we had 15 grams to work with ours, and actually we were good boys and girls and didn't even get to 13, and we managed to get our goals achieved. And they informed us on what the chemistry we should expect, what the minerals are we should expect, and how to take a deep dive into certain areas that turned out to be very important for findings, as you just talked about moments ago. Yeah.
Excellent. Now, is it true that every asteroid is the fragment of some larger parent body that got shattered early in the solar system? And I ask that because Bennu, last I checked, is bigger than the Empire State Building, something like 500 meters across. And so that seems like a big enough body to be its own body in the universe. But tell me, turn the clock back on this. Was there some protoplanet that had already sort of, as the geologists say, differentiated its materials and then shattered to become Bennu? And if that's the case, you might be able to find other rocks that are like Bennu that are out there.
Yeah, absolutely great question. First of all, the main type of meteorite we find on Earth that's like Bennu is called a CI-like meteorite. And there's only 2 handfuls of them in existence. And it's very clear from both studying the sample from Rugu and the sample from Bennu that our sample collection is biased on Earth. Not only is the sample collection contaminated, but what actually is out in space is biased because we have a lot of carbonaceous asteroids. Now, turn the clock backward. Bennu is fragments from collisions that occurred of different bodies together. One of those bodies was a parent body, as we call a previous incarnation of Bennu at a much larger scale. And that was something that was indeed, forming probably some of the early protoplanets that may have existed. And once the objects get to a certain size, around 10 kilometers or so in diameter, the internal mechanism begins to turn on for geologic process. That internal mechanism is heat begins to move around. That's generated from the decay of radioactivity and pressure.
It becomes a cosmic body at that level.
A cosmic body. It begins to melt the ices that were accreted with it. It begins to have fluid, and we call that the early stages of metamorphism in geology. And the early stages of metamorphosis, that fluid moves through and begins to interact with the minerals that are there. And it begins to change those minerals and pick up different kinds of chemicals as it's moving through the fluid. It moves in different parts of the asteroid because it cracked and all kinds of things that happen. And then what we think happened is that at some point, the poor parent body asteroid gets collided into with something else, and it stops the process. So you have a snapshot in geologic time of that moment that all the processes geologically were active, stopped.
Wow.
Because it's not big enough to sustain it anymore, and it gets frozen in that state.
It got knocked up, and it banged around, and that's it. So
yeah. So because it's relatively recent, recent in my professional life, last several decades, that we came to learn that star systems, like we take the solar system for example, with its 8 planets. Stop. That if you run the models, that star systems such as ours likely began with like 30 planets or something, or planetesimals, and many of those orbits are just unstable and they collide with each other, and it gets resolved. And so it takes a while for that to sort of shake out and find out who's left in the ring.
You just described the coolest game of billiards ever.
Yeah. Who survived?
Who survived? Survivor billiards.
And don't you even have? There's some asteroids where there look like there are 2 pieces that are stuck together that didn't break apart.
Well, yeah, there are also asteroids that have satellites that go around from collisions, most likely. So
right.
Even asteroid Bennu, although we don't have a satellite, didn't find a satellite, it was geologically active on the surface, and we had these explosions that pushed material up, which was not cometary-like. But we had looked, going back to the comet discussion, we had looked for cometary action because one of the hypotheses for Bennu before we got there was it could have been an extinct comet core. But it isn't. At least most of us will say it is.
Right. It's not a clean boundary between asteroids and comets, right?
No, sir.
Yeah.
It is not.
Yeah.
You know that better now. Yep, it is not.
Yeah. So now when we think of life, I think of we're carbon based. That's, everybody knows that. And we eat food, and we have crops, and we eat plants and animals. And I always see phosphorus showing up as some key ingredient. And not being a biologist, I've never fully come to appreciate what role that plays. So could you just tell me about phosphorus? I know it's an element on the periodic table. And did you find it in this asteroid sample? And what role does it play in sustaining life as we know it?
Right. So let's go back to, again, the square root of 1, and that phosphorus is, of course, one of the elements on the periodic table, as you said. And the accretion time period of the asteroid, you have all this material accreting, which contains all the different elements that we have on a table, to some extent, not things like hydrogen and helium and stuff. Then as time goes on, minerals start to form through the interaction of water with these rocks that we talked about. And that water is moving through with different, what I call nutrients. In this case, it's not for biological system, but geologic system. And things like sodium, like in sodium chloride, table salt, and chlorine, and phosphorus are in this fluid. And then
I love that reference, the geologic nutrients. That's a cool thought.
Well, to me, they were alive at one time.
I get okay.
Yeah.
To you, rocks are alive. That's fine.
Yeah. Don't worry. Give it time. Some influencers on the social media will be pushing geologic nutrients for your health at some point.
Oh yes.
Yeah.
I was hard when I was in high school. Let me just say that. I was a geek. Anyway. So there's a whole sequence that forms of these different minerals, the calcium-rich ones, then the phosphorus-rich ones, right? And they go down through what's left in the fluid to come out of the fluid and start forming new minerals. So you get things like sodium, etc. And phosphorus is one of those key minerals that makes things like phosphates. And of course, phosphorus is one of the key kind of elements that gets bound together with things like carbon and hydrogen, etc., to form prebiotic compounds that are important. And it's the whole suite of these evaporite minerals, not just the phosphorus. The phosphorus is critical, though, but it's not just that. It's a whole suite of them that we, as life, have to have in different ways and different proportions. Now, I'm not a biologist, so keep that in mind.
Yeah. So tell me about presolar grains. There's a lot of research papers on this. In fact, we have some on display here at the Rose Center for Earth and Space. In fact, they're presolar diamonds, I think. And there's some, and I think it's kind of cool. I just don't know its relevance. It's cool to think of grains that might have predated the formation of the solar system, which gets you even farther back than the 4.5 billion years. So I think that's kind of cool. But is it just sort of cool to know, or does it have other relevance to any of this?
Well, I mean, they're saying better than I, we are stardust. We are made up of stardust, right? And stardust means dust that literally comes from stars, either evolving stars or dying stars that eject material. And in that ejection, that gas that comes out, like the fluid with minerals condensing, these new minerals condense out of the gas. And these are from stars that are not part of our solar system, and seeded what was there in the beginning before our solar system formed, which was a molecular cloud. And there are different kinds of presolar grains. The diamonds are one of them. Yeah, downstairs in the museum's meteorite hall, there are diamonds in a little capsule in there, which is fantastic. It looks like a slip, like a grayish mixture inside of the little vial. There are silicon carbide grains, but then there are what we call corundum, or little teeny tiny, and we're talking really so small, smaller than what we can see certainly with the naked eye, nanometer size.
Isn't some of these that you're describing used as fake diamonds on Earth? Or corundum? But no, I have some memory.
That's ruby or sapphire is what that is. Yeah.
Oh, okay. All right.
Yeah,
okay.
Yeah.
And then there are silicates. Silicates being the most abundant minerals that we see on Earth, like quartz is a silicate mineral, for example. Olivine or peridot, the gemstone peridot is another one. So these grains predate the origin of the solar system, and they provided the nutrients, if you will, for the beginning of the formation of rocky materials and minerals in this solar system, because everything got crunched as the gas began to collapse to form the sun, and things heated up, and then they cooled down and stuff came out. But these grains survived that process. So they're actually older than our solar system, which is really, really cool. And there are people who spend their whole life studying these presolar grains, and it's incredible. Yeah.
So the solar system was basically able to form because it was on a whole grain diet, is what you're saying.
I love it. A whole grain diet. Vegetarian. Maybe even vegan.
Didn't he do 7 grains there? I thought there were 7 grains there.
And just one more point about the presolar grains is that we find them in the meteorites. That means they survive the geologic processes, such as the water moving through or heat beginning to generate. And many of them survive to different degrees depending on where we're getting the sample from and what was the original parent body.
Wow.
So let's pivot to other places where these search for ingredients of life have been in the news, such as Mars. Right? We're not quite there yet with Europa. We've got a nice Clipper mission en route. We have a whole episode of StarTalk where we toured the Jet Propulsion Labs and spoke to the folks. It was right around the launch time of the Europa Clipper mission to look for life with ice penetrating radar, to look under the ice, that icy moon with its ocean of liquid water. But if we go to Mars, where there's no water today, but such ample evidence that there was once running water, do you compare notes with your fellow Mars geologists or Marsologists, whatever the word is you might call them, to see? Because I remember there's a recent news where there was some inclusions in some kind of clay or something that people felt pretty sure is a record of some kind of microbial life thriving in a distant past. And there are inclusions that only a geologist would recognize as being something interesting. And then you pair that up with the biologists, and all the astronomer can do is just watch you guys have a conversation about it.
Well, you can talk to us about it as you do. yeah. But that's a great. I like the way you drew that. That's so from lessons learned from analyzing Bennu, for example, and Rugu, and there's several more papers coming out in the near future from the OSIRIS-REx mission that are going to detail even more interesting results about prebiotic compounds. So keep to the literature for that. Look for that very soon.
And just to be clear for everyone in this modern era, it means a research paper with many collaborators that has been submitted for peer review, has been revised according to whatever the peer review might have recommended. Then it shows up in the journal, online or otherwise. And that then gets disseminated around the world for others to comment on, to stand on the shoulders of what was there. That's what's going on here. He's not making a YouTube video.
Well, yeah, it's either that or he goes on Joe Rogan for 2 hours. It's either the first or Rogan for 2 hours, which is the same, by the way.
So in that area of Mars, what was it called? I forgot. Shiana Falls, was that what it was? Yeah. The minerals that were there in large veins of what are probably a mineral called gypsum and associated minerals are minerals that form through a fluid. Precipitation, they're evaporite minerals. They have to come out of this fluid that is there, and the fluid's evaporating. And other minerals that are there, such as vivianite, which is a phosphate mineral. Here we go, phosphorus again, one of the key ingredients for life.
Isn't gypsum on the Mohs scale? I have some memory of that.
You got that right.
So I got that right?
You got that right.
Gypsum is very soft. It's like one or two. Or
It's a hydrated mineral, so it has water attached to it, which makes it structure.
And then grigite is another mineral that form, and that's an iron sulfur-rich mineral. But that is an interesting mineral because it's on a pathway. The final product forming would be pyrite, which everybody knows as schools go. The mineral before that is macanalrite, big name, but that mineral was recently discovered in both Rugu and Bennu for the first time. Now, why is this mineral grigite important? Because it's sampling different abundances of oxygen that is around in order to produce itself.
Okay. Now, oxygen is not uncommon in the universe, but it's highly reactive, right? So it's going to be binding with almost everything. And so where's it getting its oxygen from? What's its source?
Oh, that's a great question. We assume it's coming from a fluid interaction, a fluid that has evolved. But how that fluid's evolving, I don't know. When that fluid evolved, I don't know. And the landscape certainly is such that fluid was moving around, water.
In the Cheva Falls, in those deposits, I don't know, is that the right word? Inclusions,
yeah.
Those, yeah.
Oh, the sedimentary rocks deposits.
Yeah. Are you convinced that there was an active biota in the distant past from that evidence? Or is there another way to explain that does not involve life? Because life would be extraordinary and fun, but, you geologists have all kinds of ways you can make stuff, even without life.
Oh, I know it. So I'm not sure if life was actually part of that process, but I'm not going to eliminate it as a scientist from that process. It could be what we call abiotic or not requiring life, but it may be that life was there. There are other evidence to suggest that and I don't know the details of the organic compounds. There's simple organic compounds that were also found there that may indicate that life was there. But as we know from working with Bennu, we're beginning to understand that the organic compounds that we're finding in Bennu are much greater than what we see in the meteorites, and the process which formed them most likely it occurred inside of a great parent body or on surface or subsurface of Mars, for example, or Earth, and that is an important punctuation point that we have to know. Meteorites are definitely contaminated, so we're learning a lot about organic chemistry in the solar system in the prebiotic chemistry from the meteorites. From the asteroid samples, that the meteorites are definitely contaminated.
So if you look at that and you look at, let's say you find these evidences on Mars, and then we already know that they're in the asteroids. Is that, I don't want to make a big leap, would that be any indication that there is this so-called Lithopanspermia that seeds planets like ours to create life? Or would it mean that, hey man, this is just the stuff that shows up under the right conditions, doesn't make a difference where you are?
Yeah, that's a great question. The latter is certainly more or less what we've kind of been leaning towards here, in that the asteroids themselves could be seeding Mars and Earth with the prebiotic compounds that are needed for life to have evolved. But I'm old enough to know that we have meteorites from Mars on the surface of Earth. And I'm old enough to know that there was a time period when certain physicists said you couldn't get rocks off of Mars to Earth. And when we finally proved that these are, essentially proved to a high level of confidence that these are from Mars, the calculations showed that you can. So it's certainly not impossible, but I mean, why go there when we can go with a more simple answer, at least at first, to eliminate that? But
So I found a fascinating concept. Let me just share it with you and tell me if you agree. So the biologist sees life on Earth, and we don't see life elsewhere as thriving as it is on Earth. So it's easy to just come up with the singular genesis of life on Earth by whatever cause. Then you have to, and we know how complex the DNA molecule is. So we can ask ourselves, could that have happened on any other surface of any other planet? And we say, look how complex it is. No, it's unlikely. However, geologic processes, I can send you to any planet and you'll be familiar. There might be some fun, interesting things you've only read about or heard about in abundance there, but geology, when you subject minerals and ingredients to the same temperatures, pressures, will get you the same results every time. So if you create a biological analog to that and say, given the right temperatures and pressures and time, you'll make a DNA molecule every time. What do you say to that? That maybe, if geology is universal,
for geology, why wouldn't it do it for us?
Why wouldn't it do it for biology? Yeah.
Yeah. The short answer is yes.
Oh, okay.
Yeah. I'm glad we cleared that up.
But I have an issue with the panspermia hypothesis.
Okay.
And by the way, that's an hypothesis surely named by men.
Oh, without a doubt.
100%.
Yeah, without a doubt.
100%.
Yeah.
Okay.
Yeah.
So life begins in one location and then spreads to other location, which, by the way, I don't think getting back to your ignorant physicist comment, I think no one knew how to do that until we can computer model major impacts on planetary surfaces that can then fling rocks back into space. And you couldn't just deduce that. You had to calculate what happens to the energy of the impactor and how it gets manifested. So in all fairness to the ignorant physicist, computers helped us out there. to the cocky physicist.
Okay,
right.
It was my chance to have fun at you.
Yeah, by the way, just further in your defense, one of our greatest physicists, Lord Kelvin, of the Kelvin temperature scale, was telling geologists said, look, we need 1 billion years to make these ravines. We need 1 billion years. And the biologists were saying, we need 1 billion years to evolve everything. And he was saying, I'm only giving you 10 million years because that's the lifetime of the sun. And there's no way we can make the sun live longer than that. And so that he got his ass handed to him when we discovered that there's thermonuclear fusion in the sun. And there's a whole other thing that was discovered after he made this proclamation. So, but he had the cockiness of a physicist, knowing that physics is pretty fundamental. So you can't.
From that day forward, nobody believed his sports predictions. He was like, I'm taking the Patriots in 30 points.
I can cry over.
So my issue with panspermia is, if you can make amino acids on rocks in space or in the parent body from which it came, you can make amino acids on Earth without the rock. Earth has got all the same ingredients and then some. So this urge to appeal to panspermia, for me, seemed less urgent. The urge was less urgent. when I look at it that way. So maybe the argument in favor of it is really, really hard to make life. So if it happens in one place, the chances are it's not going to happen in other places. And if it's going to get there, it's going to have to travel. I think that's the argument in favor of panspermia. But yeah, because if it's easy to make amino acids, but harder to make a DNA molecule, maybe that's what it comes down to.
There's one little catch to that in the sense of geology, in that the oldest rocks we have on Earth are from 4 to about 4.4 billion years, which is one of many reasons we study Bennu samples, Rugu samples, and meteorites. Because in part, the Earth is dynamic, it's active, it's moving, the surface is constantly moving, but also the very, few tens of millions of years of the Earth's existence, the surface was really molten before the crust formed. And that's what a lot of the scientific hypotheses hit at, that it was cooked too much for these kinds of compounds to survive on Earth. Now, maybe inside is another issue, and maybe the meteorites coming down and seeding after the cooling happened, either on Earth or on Mars, is much more probable now than it was, I think, before we flew both missions. And in fact, we have sugar too now. We have RNA sugars. That's a really big deal too.
Yeah, the ribose, right?
Yep.
Your sugars to go with your multigrain cereals. Kellogg's better get a handle on this one. Of course, as scientists, we need to be sort of skeptical of extraordinary claims. If life can explain some of this evidence, can you get to that same evidence by not invoking life at all?
Well, that's what we're learning from the study of Bennu samples and Rugu samples. And I can't give you an answer yes or no, but looking like a lot of the ingredients, yes, they can happen abiotically. At least the ingredients for life. What happens after life comes about, how it changes that is another issue. But that is where we're going right now.
As a person who is in front of the public explaining all of this, I have challenges because, for example, when we see methane on Mars, and we know methane is a product of anaerobic metabolism.
Better known as Mexican food.
I ain't going there.
I know, right? Yeah, I mean, it's what happens deep in your gut, right? The microbes operate anaerobically, releasing methane, and so, but yet the surface of Saturn's moon Titan has lakes of liquid methane, and so, but there are no cows on Titan that we know of. So clearly, methane is coming from non-biotic means. And so it's, to jump for joy when we see a chemical signature of something that we know can come from life. We have to be very honest about all the ways that it might not.
Yeah, I think that's also, I think, to bring it back a little bit to Bennu, I think that's why it's also so important that we know the context of what we're analyzing and understand very clearly what kind of geologic processes occurred to that particular rock or rocks. Because organic chemists, for example, they don't know geology. They don't need to know the geology, but we geologists have been very poor over the course of time at explaining what we mean when we say things are geologically processed. And it's much more complicated than what often is interpreted either by the organic chemist, biologist, or even, the general public. So we have to be very careful about that.
Now, at the beginning of this conversation, you mentioned the possibility or being cautious about a rock that might hit Earth by 2200. I don't think you pulled that number out of your ass. Bennu in
not this time. Not this time.
Either way, whether you pulled it out of your ass or not, either way, good luck to those people. I mean, I'm good. You say 2200? Okay.
Yeah. You're out of the picture by then. But the next close encounter, if my records are correct, is in 2182 for Bennu, and given our orbital uncertainties, I think there's a chance it could hit Earth in 2182. That should be plenty of time to build a defense system to deflect it. It should be, unless funding continues to wane.
Oh, then we're screwed.
But as geologists, you probably don't think much about asteroid collisions the way the astronomers do. Is that correct?
Probably. We look at what's left over.
Okay, that's very blunt. That was very blunt there, Harold.
Oh, that's awesome. Hey, look. When life gives you lemons, right? What are you gonna do?
Yeah. Dizzy. I'm laughing so hard. Okay, yeah.
So the probability that I last remembered, maybe it's been refined since I last checked it.
You're absolutely right, Neil. Yeah.
It was a 1 in 2,700 chance of hitting Earth in September of 2182.
And as they said, that's a non-zero chance.
A non-zero. And it sounds
who cares?
It sounds like, oh, that won't happen then. But there are people who go to Vegas betting on way worse odds than that, expecting to win. So these are near-Earth asteroids that we want to keep an eye on. And the more we know about them, the more we can maybe go back to them in the future and nudge them out of harm's way.
That's right. 100%. You got it. Yep. Now that we understand the composition better, that's a refined value that you gave, and that's probably as accurate as we're going to get, which is pretty accurate because I think it's September 24th of that year. The prediction is. So that's pretty accurate, but I may be wrong. But
yeah. Just to bring this to closure, could you just reflect on where you guys are as geologists when I think of the history of collaborations? If we go back before 1968 and the photo of Earthrise over the lunar surface, it was not until NOAA was founded in the year 1970 that I ever saw the ocean and the atmosphere in the same phrase. NOAA is National Oceanic and Atmospheric Administration. And my sense was they were ocean scientists and they were atmosphere scientists. And of course, you have geologists on the land. And then as time moved on, the interplay of these major forces on Earth's surface required you guys to play nice in the sandbox. And then eventually we find, is it more than half of the biotic mass on Earth is below Earth's surface? There's some staggering fraction of the mass of biology below Earth's surface, which means the geologist has to walk in the room and have something to say about that. So could you just reflect on the state of collaborations among the biologists, the geologists, and of course the astrofolk today?
Right. I think because of these sample return missions and other space missions, we're really an exciting time period in our history. And the way to get to this is simply talk about the connection between life and prebiotic compounds. We know life exists. We know that the prebiotic compounds exist, and there's a gap between the two. How do you get from one to the other, right? And in the middle of that gap, we know you need things like oxygen, you need water, you need energy. But everybody forgets that to get that, what you need is a planet. And understanding how planets are formed and the baseline geology that then the final baseline below geology, the physics can all play into, and then work with the astronomers, the remote sensors, the biologists to put our various hypotheses together to test them with our knowledge in a big picture scope.
Because, of course, the universe doesn't care about how we have divided our sciences. The universe is just the universe.
True. That's very true.
It's our problem that we have walls between the offices of what we study.
Yeah.
Well, Howard, this has been a delight for you to participate in this conversation. I've long wanted to do a show on Bennu, and because it's been in the news a bit now. So I'm glad we could speak about it with the benefit of the analysis that has been ongoing. And just to toot the horns of scientists, I presume that parts of your sample return from Bennu have been shared with other labs so that whatever your results are could be verified.
Right. Yeah. So NASA archives about 70% of the sample. The sample team, analysis team, doesn't get more than a very small amount of a total sample. And then we had it exclusively for a 2-year period. And then the community at large, scientists at large, begin to apply for samples at Johnson Space Center, that they can look up samples in the catalog. And then they're all currently, those people who have samples from around the world are that are not part of the science team for OSIRIS-REx, but our team at Global too, are analyzing the sample as we speak, and several papers have already been submitted to those scientific journals to talk about their findings in print. And yeah, it's incredible. And
that's how science works.
Science works. Our government shared sample with the Japanese government as well, and our Japanese colleagues, meaning OSIRIS-REx sample and Hayabusa sample, were shared, and each nation is also looking at their samples as well. So it's great.
Wow. Impressive.
That's how science works. The path to objective truths in this world is not from any one lab. It is from
it can't be
checking your ass. Okay.
That's right. That's the creative process. That's exactly right. Yeah.
Thanks for actually setting the example that none of us are going to follow.
Well, good luck for this. And what will you be doing in London? You're headed off there now?
Yeah, first let me say thank you very much for the invitation and to join you both. It's been a lot of fun, and I've learned a lot myself, and I really appreciate your kindness. And I'm going to London for a 3-month stay at the Natural History Museum in London. We'll be going back to the square root of one and taking what we learned from studying asteroid Bennu and asteroid Rugu samples back into the lab and looking at our meteorite collections. And then I'll be doing a bunch of lectures around the UK as well on OSIRIS-REx. So it's time to go have a little bit of rest and recharge the batteries.
Very nice. Very nice.
And where's our best source to keep current with Bennu? Is there a JPL have a page on that, or is it Johnson? Or do you have a page from your lab that you co-founded?
Yeah, I post some things on my website, and generally different members of the team. We have no centralized area other than NASA making its usual posts about what we find. So, and
your website is what?
Oh, it's Harold Connolly at WordPress.com. Yeah.
WordPress. Okay.
Yeah, thank you.
All good, sir.
I try to keep it updated, but I'm bad at it.
Excellent. Thank you for this. Chuck, we're done here.
Well, this was great, I have to say. I've learned more about Bennu than I ever thought I would, and I'm happy that I did.
And I learned that you don't care if it hits Earth in September 2182.
Yeah, I'm good.
Not 2182.
Yeah, first of all, let me just tell you something. If it does, my only regret is that I can't do my own touch and go mission where I collect nothing but spray paint "Hello, dumbasses" on the side of the asteroid.
For not deflecting me.
Right. You've had all this time to do something.
You had all this time.
You're screwing it up, you morons.
All right. That's all the time we have. Harold Connolly, Jr., thanks for participating.
Nice to meet you, Chuck. Thank you so much.
Chuck, always good to have you, man.
Always a pleasure.
This has been StarTalk, the Bennu edition. Until next time, I bid you to keep looking up.